There, astronomy pals. Here's a video to walk you through some of the details that are related to this quiz about conjunctions and parallax. So a conjunction is when we see a bunch of planets, or even just two planets, like quite close to each other in the sky, even though we know they're really far apart. And we have to think about on this quiz. We need to think about like why that happens, why we see that, and it connects to the orbits of the different planets, because each of these planets is on its own like sort of circular orbit, like we've talked about. But one way to think about it is what the same thing that we discussed in class, related to like how it's possible when you shift your head, or in this case, when you shift a camera, to see these objects shift position in the way they do. And we talked about how when I actually took these pictures, the three objects were in line with each other. And if I had been in the middle, if I'd put my camera in the middle, they would have looked like they were all on top of each other. But because I'm shifting the camera from the left side to the right side, we see something called a parallax shift. We see the objects like kind of like move at different angles depending on how close they are to your eye. So I wanted to show you a couple of these examples. We see this example on slide 1 of this checkpoint with three objects: a chair pretty far away, and then a lamp, and then a pencil that's closest to you. And you can actually see this if you look at three objects that are like basically in a line. If you look at them with your left eye, then your right eye, and you kind of like go back and forth between them, you'll see a shift. Now, if you were looking in the center, that is, like if your eye was in the middle, this is what you would see. So we can see like all three of these objects are basically on top of each other. In the case of planets, they don't necessarily have to be exactly on top of each other, just really close. But if we move our head to the left, or if we look at it with our left eye when our nose is in the center, we're going to see these objects shift. And these dotted lines help us figure out how much we're going to see the object shift by. So for example, this dotted line shows me I'm going to see the pencil at an angle of 24 degrees to the right. So I'm actually not going to see the pencil in the center. The pencil's going to be over here, 24 degrees to the right. I can tell that I'm not going to see the lamp in the center either. I'm going to see it at 8 degrees to the right. So I can drag it over to 8 degrees to the right. And the chair is actually, looks like it's pretty close to 0 degrees. But maybe the chair is like a tiny bit shifted to the right. If I'm looking at it from my right eye, it would basically be the exact opposite. The pencil would be at negative 24 degrees, the lamp would be at negative 8 degrees, and the chair might be a little bit shifted. So I can move the pencil over here, move the lamp over here, and then the chair is like pretty close to the center, but maybe I move it a tiny bit to the left. So like this would be what it looks like when I use my left eye and then my right eye, and my left eye and my right eye. So like this is something that you should actually see for yourself in order to understand exactly what I'm talking about. Now, the trickier thing comes into play when we have to deal with trigonometry to figure out how far away something actually is. We can use like triangle math tricks to figure out how far away this pencil is, or the lamp is. And we're using a function called tangent. You've probably seen this in math before: sine, cosine, and tangent. Sometimes people ask you to remember, they put it on this page, SOHCAHTOA, because sine stands for opposite over hypotenuse, etc. All of these, sine, cosine, and tangent, are basically describing ratios of triangle sides. So what we're saying is, if we look at tangent specifically, tangent is opposite over adjacent, meaning it's the opposite number of the side length over the adjacent side length. Opposite means like the farthest side from the angle, and adjacent means the closest side to the angle. This longer side has its own special name, which is the hypotenuse. So if we leave this on tangent, notice like if I move these around, the angle changes and the ratio changes. Like 10.97 over 19 is 0.57. Or if I make the angle smaller, 5.4 over 19 is 0.287. So these are things that a calculator can figure out for you, and they tend to be really useful for solving problems in the real world. So that's what we want to think about here. Let me walk you through a problem using the actual tangent, and then I'm going to show you the small angle approximation because it is even easier than using tangent. Using tangent is not so hard, but the small angle approximation is even better. So if I write tangent of, in this case I'm trying to figure out how far it is to the lamp, so I can see I've got this triangle here that includes the angle 8 degrees that we were figuring out before, because we said, okay, the lamp is at 8 degrees. We see it shift 8 degrees left or right when we look at it with our left or our right eye. So tangent of, in this case, 8 degrees equals 5 centimeters, the opposite side, divided by this distance, which I'm going to call d. Basically, we're trying to figure out how far it is from our eyes to the lamp. So tangent of 8 degrees equals 5 centimeters over d. Then all I have to do is solve for d. So my first step would be multiply both sides by d. So I'd get d times tangent of 8 degrees equals 5 centimeters. And then I need to divide both sides by tangent of 8, oops, not that, tangent of 8 centimeters, tangent of 8 degrees. And then I would get d equals whatever 5 divided by tangent of 8 degrees is. So I can actually do that up here. I can say 5 equals 5 divided by parentheses tangent 8. But I do need to write degrees if I want Google to understand that. I'll tell you why in a second, but there's two different ways of expressing the angle, and Google will understand if you write degrees, or maybe even if you write DEG. Will it understand? Yeah, so it understands degrees as 8 degrees. So if you write tangent 8 degrees or 8 DEG, it understands how to deal with that. So we know, okay, 5 divided by a tangent of 8 degrees equals 35.5 centimeters. We're saying this lamp is 35.5 centimeters away from our eyes. Now, I told you I'd show you how to do the small angle approximation. And the small angle approximation uses a special trick involving this other way of expressing angles. So notice there are two different numbers on this slide. There's the degree angle measurement, and then there's this number below it, which is called a radians angle measurement. And you may learn more about the difference between degrees and radians in math class. Some of you may already know about it, but we're not going to talk about it here. Mostly, you need to know that there are basically two different ways of measuring an angle. So, for example, if I ask Google, convert 8 degrees to radians, it'll tell me that that is 0.14. Or if I say convert 24 degrees to radians, it'll tell me that it's 0.42 approximately. So this is another way of measuring an angle. And if we use radians, only if we use radians, then the tangent of the angle is equal to the angle itself for really small angles. So check this out. If I use radians and I say, okay, what is the tan of 0.1 radians? Notice it's about 0.1. Or if I ask, what is the tangent of 0.03 radians. It's about 0.03. So this is super convenient because I don't have to deal with tangents at all, actually. If I'm using the small angle approximation, I can just assume that the tangent of, say, in this case, 0.14 is equal to the angle itself. So I can just like get rid of the tangent completely and say, okay, 0.14 equals 5 centimeters divided by distance. And then I can solve in exactly the same way that I did before, multiply both sides by d, and then divide both sides by 0.14, divided by 0.14, divided by 0.14, and I solve this out, and let me get out my calculator and just see what is 5 divided by 0.14. It's about 35, or 35.7, it said. So we get basically the same answer. Both of these are totally correct ways of doing it. Just know if you're going to use the small angle approximation, you have to use radians, meaning that's the one in purple. Where'd my purple go? Yeah, that's going to be the angle measurement in purple, not the angle measurement in degrees. So how does this connect to the power focus area? Well, the power focus area asks you to use this parallax phenomenon to figure out how far away Mars is. It describes a situation that's like actually possible. You could actually do this. And you need to do a similar calculation. Notice it gives you an angle in degrees and an angle in radians. The angle is really, really, really small, so you can use the small angle approximation if you want to. And then you'll end up with a distance between Earth and Mars as your calculation. Now, this question here, I just wanted to speak to it for a moment because it's kind of weird. It's asking you, describe or explain how your work is consistent with the other models that you've drawn. And a really good way of doing that is to think about how this calculation would change if Mars was closer to the Earth, or if you did a similar calculation for a different planet that was closer or farther away. You should be able to look at this diagram when you draw it and figure out which planet is closer, which planet is farther away. If, for example, if I was going to try to do that same calculation in this example for the pencil, I would use a different angle. So I'd use 24 degrees or 0.42 radians. Let's try that really quick to see how it works. Now, so instead of using, let me just like, I'm gonna make my drawing work here just a second. Instead of using the angle to the lamp, we're going to use the angle to the pencil instead. And remember, the small angle approximation makes it super easy. So I'm going to actually use 0.42 radians equals 5 centimeters divided by distance. I'm going to replace this 0.14 with 0.42, divide by 0.42 on both sides. And let's do this division problem real quick. 5 centimeters divided by 0.42 equals 11.9, or 12 centimeters. So we're saying this calculation shows us that the pencil is closer than the lamp. Because the pencil is closer than the lamp, the pencil shifts more. It shifts a greater degree from the left eye to the right eye. And that's a great explanation for how I know my calculation is consistent with the real life situation. So I could, for example, if I was using these sentence stems, I could say, if I did a similar calculation for the pencil instead of the lamp, then I would get a smaller number for distance. That assures me that I'm doing the right thing, that my work is consistent. So hopefully that's helpful. You can do plenty more practice in these other slides, and these other slides are going to end up being a grade as well. It's that important. Then it'll take you to slide 13. If you want to get the highest score possible on this, then you need to document a parallax shift of your own, kind of like I did with the coffee pot and the crackers. And you need to calculate how far those things are apart from me. How far those are away from you or away from your camera. So hopefully there's enough here to help you get a lot of good work done on that. And thanks for watching.